or at least in my version of the textbook, x minus x naught squared plus y minus y naught squared plus z minus z naught squared equal to a squared. I don't know why you wouldn't use an r over there, but they use an a. Is the equation of a sphere. So one of the words I'd never be saying. A sphere with center x naught, y naught, z naught, and radius a. So that is our equation of the sphere. And the reason this works is because of how the distance formula works, right? If you have a sphere and the center is, let's actually pick, oh man, I just got to pick up all of a sudden. Let's actually pick a point like -1, 0. And the radius is, let's say, 5. Well, when you're talking about a sphere, just like a circle, a sphere is all points in 3 dimensions, if there are 2 dimensions, that are the same distance from this one center point. So any point on the sphere, let's call it x, y, z, is such that the distance between any point on the sphere and the center is 5. So the distance between 2 points in 3 dimensions, or really 8 dimensions, but 3 dimensions typically, distance is the square root of the difference in each coordinate squared added together. So it's x minus 2 squared plus y minus -1 squared plus z minus 0 squared. And that's going to equal 5 because the distance we want to be is 5. And then we're going to square both sides and we're going to get, oh yeah, x minus 2 squared plus y plus 1 squared plus z squared, right? We're not going to write z minus 0 squared. That's silly. Is 5 squared. So yeah, right? You're describing a sphere when you say, oh, I want all the points that are equidistant or the same distance from to -1, 0. And I want the distance to be the square root of 25, which is 5. So yeah, that's a sphere. But then, oh, I guess before I should end then. Also, we can talk about setting things equal to things. So for example, right, like if I want to say what y equal to 5 is, well, let's think 2 dimensions first of all. If I was graphing y equals 5 in 2 dimensions, I'd get a line. The way I kind of think about it is I've lost a degree of freedom here, right? If I just said nothing, you would say you have the whole plane. But y equals 5 limits what y can be. But since I've said nothing about x, x has unlimited potential. X could be any positive number, any negative number. So we get the entire gamut of x values when y is 5. Well, in 3 dimensions, if you say y equals 5, x and z are both free to roam, meaning in 3 dimensions, let's try using some different colors here. If I go over 1, 2, 3, 4, 5, there's y equals 5. But y equals 5, then x can go in any amount backwards and forwards, and z can also go any amount up or down. So you actually get an entire plane's worth of results. Sorry, my planes are not going to look that good, because you know, it's me drawing. Right, you get an entire plane where the y value isn't changing, but the x and z values can be anything. Right, so you could have the point on the plane 0, 5, 0, or you could have the point on the plane, if you go in the x direction, maybe I go 3 in the x direction, 3, 5, 0, or I can go up, maybe 4 to 0, 5, 4, or I can go over and up, right, to like here, where I'm at, sorry, I know it's getting messy, right? That's the point, 3, 5, 6. But anywhere in that plane, the y value is 5. So if I say y equal to 5, I still have 2 degrees of freedom or 2 directions of motion that are kind of unaccounted for because my equation doesn't have any x's in it. It doesn't have any y's in it, or z in it, sorry. So yeah, if you just have something equal to 5, one variable equal to a number, you have a plane that is essentially parallel to the other 2 axes, right? This plane y equals 5 is parallel to the xz plane that you get by just taking the one where y equals 0. And in fact, that's actually worth mentioning as well, right? In 3 dimensions, right? The bottom plane here, or right, this plane here, xy plane, is when z equals 0, and x and y are unaccounted for. The yz plane, which is yz. So let's do the yz plane is the one that kind of is flat on the board, right? So here's the yz plane. Hopefully you guys can kind of see this. Again, I know the drawings are not always great. And then the xz plane would be the one that kind of is cutting out towards you, right? It's going to look like this one here. Again, I know the pictures are not excellent. I'll try and stop apologizing for them because they are what they are. So, how do I say this? Basically, you can just have x, y, and z to the first or 0th power, meaning you don't have them. That's going to be a plane. So you could have, you also have a plane when you have 2 variables, like, for example, the equation x plus y equal to 4. That's also going to give you a plane. You're going to find, because essentially you're drawing a line in one of the planes. So right, I don't have a z, so I'm going to look in the plane z equals 0. So here's the line. Y equals x plus 4. But sorry, y equals x. Y equals x, not y equals x plus 4. Y equals, no, it's y equals negative x plus 4. Sorry. Let's just stick with x plus y equals 4, James. Come on. But z can be anything, so we can go up or down, right, as much as we want. Again, I don't recommend drawing these unless you have to. I mean, you've kind of got this plane that isn't flat, but kind of like tilted this way. It's kind of like that's I know not super helpful. So basically, if you've got x, y, x and or y and or z to the first power, you're gonna have a plane. It's also true if you have like x plus y plus z equals 2 or 3x, right? Any just, let me just say this: ax plus by plus cz equal to d is the equation plane. And the only thing that's required is that at least one of these coefficients is not 0. So either a is not 0, or b is not 0, or c is not 0. If they're all 0, then you don't have anything, right? You have 0 equals 0 as long as the results are right. You have to have at least something. That's going to give you, so that's going to give you a plane when all the powers of x, y, and z are 1, or if you're not there. Okay, planes, spheres. Again, take to heart, when you're missing a variable, that means you can extend as much as you want in the direction of that variable's axis. So yeah. Some more examples of this would be something like, oh yeah, I got some good examples in my brain. Something like the following. Let's see. I'm going to try and think of stuff I can draw without too much challenge. Let me actually, I'm going to cherry pick one of these ones here. Sure, yeah. I'm gonna do one. This is kind of like number 6. X minus 8 squared plus y minus 9 squared. And yeah. Interesting. So we're getting a little, so this is less than or equal to 3. Less than or equal to is interesting. And we have z between -1 and 4. All right, let's ignore the less than or equal to for just a second. Let's just ask ourselves, what if this was equal to instead? So if you had this kind of thing squared, x minus 8 squared plus y minus 9 squared equal to 3 in 2 dimensions, right? Let's ignore the z for a second. What kind of shape do we have? Everybody, I know you guys know what it is. I just don't want to say anything. Right, it's a circle. Circle with a center of 8, 9, and a radius of square root of 3, which is annoying, but it's what we got. So if I were to draw this, yeah, I'll draw it. So x, y, let's pretend 8, 9 is like, we'll take it over here. So there's 8, 9. Square root of 3 is like 1.7, so right, it's a pretty small radius. So the equal sign is the red, right? And I know it's not a perfect picture. There's my circle, center, 8, 9, radius, square root of 3. But if I want x minus 8 squared plus y minus 9 squared to be less than or equal to 3, I want to be inside the circle. If you're not sure if you're inside or outside, test the point. I usually test the center. If I test the point 8, 9, 8 minus 8 squared plus y minus 9 minus 9 squared is 0 plus 0, and that is less than or equal to 3. So if your point satisfies the inequality, then everything on that side of your boundary also satisfies the inequality. So everything. But then we also want to extend it in the z direction, right? So I want this circle, but I want to go 4 in the positive z direction and 1 in the negative z direction. Now, right-hand rule time, which way is the z-axis positive? Is it towards you or is it away from you? Well, fingers along the x-axis, curl them towards the y-axis, your thumb points in the positive z-axis. So the positive z-axis would be coming up this way. So we would extend the circle in each direction, and we get a cylinder. Right, we're essentially going to say we're going to move this. Now, let's see, I'm trying to do it, not terrible. We're going to move this. Right, so right here, sure. The center there would be 8, 9, 0. And the center here, just moving it 4 in the z direction, would be 8, 9, 4. And moving it 1 back in the z direction. Right, and maybe. And then I guess we would like color it all in. So what have I got here? I've got a cylinder, right? If you want to draw it in the more like normal orientation, again, I know we're not being asked to draw these things, but I'm trying to see what they look like. We'd go out 8 over 9. So there's the center of our circle. And then so there's my radius maybe of the square root of 3. And then we know we're going to go up 4 and down 1. Right? So it's a circle, right? It's that circle, but I'm drawing it now. Now I'm drawing red. So there's the circle in the XY plane, right? That circle is that circle there. And then Z is allowed to go up 4 and down 1. So it's all of that. And so I want to be really, really clear here. It's not just the boundary. It's actually all of the volume inside of the cylinder. because it is x minus z squared plus y minus x squared less than or equal to 3, meaning you get everything in the circle, and z between 1 and -4. Sorry, -1 and +4. So if everything as low as that up to z. Okay, so you get, it's instead of the cylinder being empty, it's full of water, and all of the water is what we want, including the boundary. Hopefully that's, so typically when you have something less than or equal to or greater than or equal to, you're describing all of the stuff either, usually hopefully inside, because inside usually makes more sense, but sometimes it's all just outside. Yeah. Oh, I had another example. Yeah. Let's look at something a little different. Oh, what is this? There's a name. It's a name I forgot. Okay, I'm forgetting all things. Let me see one thing real quick, because I know the name for this. Boy, I should know the name for this. What I'm really trying to say. Where'd you go? 3D graphing, yeah. That's not what I wanted. There we go. Where's the name I'm looking for? Here are some nice pictures that Grant has drawn that I'm gonna throw in the chat just so you guys can look at them. I do think they're nicely drawn, so they might help you see things better. You can take a look at that if you want. The word I'm looking for, though, is not showing up. The word I'm looking for is the word you use when you have a parabola, but you've like extended it, or basically any shape. Let me see if the book, I feel like the book does not talk about this, but I feel like it's a word that's important to know. I feel like it's just called a cylinder. Although I know that's kind of weird to think about, but okay. Can't stress too much about it. So what if I wanted to graph y equals x squared? Y equals x? Sure, y equals x squared. So I mean, in 2 dimensions, super easy. In 3 dimensions, it's a little bit harder. So we've got the parabola. Right? So I'm trying to draw 2 points here. So I get the point 0, 0, right? X is 0, y is 0. I get the point 1, 1. Right, not this way. Yeah, that's not right. I get the point 2, 4. So we can go like that. Like that. All right, it's supposed to be in the xy plane. So you have to have to be kind of flat. And then the same kind of thing this way. It's always hard to get the perspective right on these. There's my parabola in the xy plane, but then I'm going to extend it as much as we want in the z direction. Yeah, sure, okay, fine. Is that about the same as that? Yeah, close enough. And then that, okay, sure. All right, so, yeah, sorry. It's hard to make this work out right. I want it to be, oh gosh, brain. Work, brain, work. All right, I can just do it like this. Sure. I'll be that much further down. Okay, cool. And then on the back side here. And then same kind of deal up here. Right, this might not fit so well. Maybe I should cut off some of this top part here. I'll make it nicer. Sorry, we're like this. Sure, right up there. Okay, fine. And there, maybe not so great. Hopefully, you guys kind of get the idea. Right, it's like the parabola, but it's kind of like a sheet of paper that's been kind of like folded around. Right, in fact, literally, they do have paper. It's kind of like you take the paper, right? You said, let's see, let me get the point. Right, here's my parabola. Right, super fun, right? So there's my parabola. You can't really see it. but you can see this. All right. So again, the idea here is that if you're missing a variable, you get to extend in that direction. We could have made it a little more interesting. Maybe not more interesting. We could have said x equals y squared and then given the condition on z as well. Like we could have said z is between, I'm going to try and make it look like what I've already got here. Let's say this is -3 and this is +5. We could have said z is between -3 and 5. Or if we wanted to just have a parabola and not a, holy crap, I wish I know what you actually call this thing. I really feel like it's called a parabolic cylinder. Now I have to, I'm sorry. Sorry guys. My brain isn't working, so I have to look it up. You guys are like, what's new? Yes, it is called a parabolic cylinder. So typically, yeah, when you take something in 2 dimensions, you just kind of extend it in the direction of the 3rd dimension that it's not defined in. You typically just call that a cylinder, I think. Let me double check though, because I want to be absolutely sure about that. Yeah. Yeah, okay, sorry. Anyway. Now I lost my spot. Okay. So I could also have said something interesting. What if I just, well, y equals x squared and z equal to 2. So now I don't get a whole range of values. I just get z equal to a specific value. So I actually have to go up to like, right? And so here's z equal to 2. So then I'm just getting right, that parabola is actually all I get if I define it this way. Right? I get the parabola y equals x squared at a point z equals 2. Okay. But let's go back to kind of the tangent here, because there are some other surfaces I would like to kind of maybe help you guys describe. I keep trying to click on this thing like I can. So, sure. Look at a few more things. Then, I don't know. Let's see, what have I got here? So actually, let's look at this one that I'm going to modify a little bit. Let's say we had x greater than or equal to 0, y equal to 4, z greater than or equal to 0. Okay, I'm going to ignore this for a minute and say, well, if x is greater than 0 and z is greater than 0, then I'm in kind of the first quadrant of the xz plane. So I'm looking at the xz plane, right? So here's z, here's x, y. X can be positive, so I can be this way. Z can be positive, so I can be this way. So I've kind of got the whole first quadrant of the xz plane, but then y equals 4, so I have to shift it over 4. So what I've actually got is we can go up in this direction as much as we want, and we can go out in this direction as much as we want. So just trying to draw a part that doesn't overlap. Right, we're essentially saying we've got this plane here along where, right, this point here is 0, 4, 0, right? We can go as much on the plane y equals 4, but only in the positive z direction and the positive x direction. We can't go back, we can't go down. So I don't know, I wasn't able to see what the options were, but for like a problem like this, to just right, because it's the problem that was posted was choose the correct geometric description of the set of points in space whose coordinates satisfy the given combinations of inequalities and equations. Oh, and see if you can sketch it all. Like I said, it'd be cool. So I would say they're probably describing this as like a quarter of a plane. Thanks. Let me take a look at that. Canvas. I'm just curious because I know there's probably like a bajillion options. Let's see, announcement, discussions. Let me see here. Okay. Oh yeah. Half plane, quadrant of a plane, half space, octant, ball, half, oh my God, ball, half ball, quarter ball, disc, half disc. Okay, region outside ball, plane minus disc, the ball minus a smaller ball. Wow, they really get into it. So this one, I would definitely describe as a quadrant of a plane. The previous one, sorry, this one actually isn't one of the, I guess it's none of the above, because this isn't one that they gave you guys, I just thought you should see it. But the previous one they're doing, the cylinder one of the options given, it would be a finite cylinder, right? Because it does end at z equals 4 and z equals -1. But let's look at a few more because there are some interesting options. Like, in fact, let's look at this one. X bigger than or equal to 0, z bigger than or equal to 0, and y less than or equal to 0. So basically, you cut your three-dimensional space in half 3 times. Half of a half of a half is an eighth, which is an octant. So, right, if you're doing this kind of deal, x is positive, z is positive, y is negative, you're limiting yourself to everything over here, which I know is, again, it's weird to draw this stuff, but right, you've got 1/8 of the entire three-dimensional space, 1 octant. I don't, by the way, I don't know if there's a specific way of numbering the octants, right? Like quadrants, we totally number, right? 1, 2, 3, 4, we go start at 1, and then we go counterclockwise. Octants, I don't think there's a specific numbering, except the first octant is definitely the one where everything is positive. So this octant here, where z is positive, x is positive, and y is positive, if we do it on this side, that is the first octant. I couldn't tell you what the second octant was. Yeah, I don't really know. It's okay, it doesn't matter. I would guess it's the one back here if we had to pick, but we don't have to. So, and I don't really think there's a naming convention for them. Let's look at a few other examples though, because this stuff is just, it's hard to get a grasp on. And I would say use whatever tools you have at your disposal. What was the cylinder one name again? It was a cylinder, but it was a finite cylinder, right? Because the top and bottom ended. So there's a difference between, I'm going to make it a little more simple. Something like, sure, let's do this one. X squared plus z squared equal to 9 versus x squared plus z squared equal to 9, and y is between a couple things like 0 and 5. This one, y isn't given. So that means it's infinite because when we draw this thing, right, x squared plus what, z squared equals 9 is a circle centered at the origin of radius 3 in the x, z plane. Right, we're typically using this convention, right, x, y, z like this. So, right, that's looking kind of like, so there's my circle in the xz plane, radius 3. And then here is what would be if I was doing this. If I was doing x between 0 and 5, I would go all the way out to y equals 5. So, you know, 1, 2, 3, 4, 5. And then we go boom, boom, boom. Just like that, boom, boom, boom. Now I start saying boom, 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 I can't stop. And there's my finite cylinder that starts at y equals 0 and ends at y equals 5. But if it was this, there's no start and end, so it just keeps going. I could even if it was, so I should say, if it was just y greater than or equal to 0, then you would have something like this, where it's an infinite, but it might be like half. You might someone might describe it as half of an infinite cylinder. I don't actually know. Probably. But then if you don't have any of this, if you just have that, then it goes forever and ever and ever in each direction. It's an infinite cylinder. Basically, a cylinder is just a circle, and then the third dimension is allowed to go in whatever direction you want. And if there's and it's not given bounds, it's infinite. If it's given bounds, it's finite. Let's look at some other strange things. What time is it? I have a good time. So I always think it's weird when they do like one of these. So I'm going to do something dumb, and then we'll fix it. Let's say we had something like x plus 4 squared plus y minus 3 squared plus z minus 5 squared is what the radius could be. I don't know, less than or equal to, I'm going to pick something not silly, 16. And x is bigger than or equal to -4. Okay, so obviously this is a sphere. Sphere with center -4, 3, 5. Oh, sorry, I said I was doing something dumb. I didn't do something dumb here, it's fine. So there's a sphere. Great, I can draw a circle and then make it look like it's a sphere. And then here's the center, where x is -4, y is 3, z is 5. And if we're keeping the convention, so then I'm going to draw my origin, right? I'm going to draw the coordinate system through here to kind of help us see what's going on. All right, so there's my coordinate system. And right, it's intersecting. Here's the thing, if x is bigger than or equal to -4, that means we're on the side of x that is that way towards you, right? This way is x getting bigger, that way is x getting smaller. This way is z getting bigger, this way is z getting smaller, this way is y getting bigger, this way is y getting smaller. So if x is bigger than or equal to -4, we essentially have the front half of the sphere. Right, we're just looking at that, and we have nothing, we have none of the back part there. So when they're describing that kind of thing, they're basically saying you've got a sphere, but then you're only getting, and it has to be like, if I had said something silly, like x is bigger than or equal to -3, that would be weird. Because then I wouldn't have the entire sphere, because right, the radius is 4, so x can be as small as -8 and as big as 0. But if x is -3, that means I don't quite have the whole sphere. The whole hemisphere, the whole half a sphere. I have less than half of the sphere, and that's not an option here. But like, if someone said something like this, you'd be like, well, I don't have the whole sphere. I don't have half the sphere. I have less than half the sphere. Because, right, half would be -4 to 0. The other half would be -8 to -4. So bigger than -3 means -3 to how far can you get to 0? That's enough. That's probably not going to ever come up, but what other kind of weirdness do we have? Let's take a look real quick here. There's a cube. 14 is a cube, if you're looking at. Basically, if x, y, and z all have limitations. I know that's not very well said. So if I said something like x is between 0 and 5, and z is between, I'm going to make it silly, 0 and 4, and y is between 0 and 3, it wouldn't actually be a cube because not all the sides are the same length. Then you'd have, right, x to the 5, y going up to 1, 2, 3, z going up to 1, 2, 3, 4. You'd have a box, or if you want the more mathematical term, well, you can call it a three-dimensional rectangle, but the actual term is a parallelepiped, right? P-A-R-A-L-L-E-L-P-I-P-E-D. Three-dimensional rectangle. Or a prism, if you like. Yeah. What else do I want to say? Oh, okay, a couple more dumb ones. Sorry, I know none of these are dumb. They just feel kind of silly to describe. What if I said my equation was z is greater than or equal to 0? Well, then I have the whole top half of space. So I have half of space, right? That's kind of silly, but it's what you've got. Or if I said z is greater than or equal to 0 and y is equal to 0 and x is equal to 1. Let me make sure I'm not saying something idiotic here. Well, so I actually am not sure what I'm saying. Let's see what I might be saying something idiotic that happens more often than you might guess. So x equal to 1 and y equal to 0. So there's the point 1, 0, 0. And then I want z to be positive. So I think I might have said something dumb. That's all right. I think I've got all of this. All right, if y equals 0, I can't go left or right. If x equals 1, I can't go backwards or forwards. And if z is positive, I have to go this way. So I have a half a line. I was trying to get half a plane. So I need to get half a plane. I think I need not to say anything about y. Because now x is equal to 1, so I still need x to be, right, I need to be not moving forwards or backwards. But now that y doesn't have the condition, I can totally move left or right. So yeah, I have half of them, right? I don't have the bottom half of it, but I do have the top half of it. One or two more things. Actually, yeah, let's just do this. We can be smart here. So if I did this, 1 is less than or equal to x plus 4 squared plus y minus 3 squared plus z minus 5 squared less than 16. Now I've got, how would you describe that? There's a word, there's a shape I want to say instead of just saying what it actually is. It's a ball minus a ball, right? It's a bigger ball minus the center. It's like if you took the Earth and took out its molten core, right? You've got a big ball, but you've moved the middle, right? Because this equal to 1 is a sphere with the same center of radius 1. This equal to 16 is a sphere with the same center of radius 4. You're taking this radius 4 sphere and you're, I know it's nicely, and you're taking out the radius 1 sphere. Right? That's what we've got. You've got all the stuff in between the black and the red sphere. There's got to be a good like real object in the world that's like a ball minus a ball. I don't know. Like a god, like I'm like everything I'm trying to think of is like a thing with the center removed. Like that. Yeah. Okay. I really feel like there's a thing. Oh well. You guys, if you figure something out, let me know. If you're like James, there's totally this kind of sphere with doesn't have a middle in it because yeah. I'm trying to think of like baked goods or candies. That's what it is. Right? All right. I feel like we've done this to death. One more. Two more. I got two more for you. So first, this one. What if I had x minus 1 squared plus y minus 2 squared plus z plus 5 squared greater than or equal to 9. Well, that's everything outside of the sphere. So it's all of space except for what's inside the sphere. It does include the boundary of the sphere still. If it was strictly greater, then it would just be everything outside of the sphere. And the last thing is, what if we had instead, but we also have x greater than or equal to 1 and y less than or equal to 2. Well, you've got a sphere centered at 1, 2, -5 with radius 3, but now you've only got the front half of it, and you've only got the left half of it, because y is less than or equal to the center. So you've got half of half, that's a quarter of the sphere. Right, so you've got this sphere centered at the point 1, at the point 1, 2, -5. Let's unfind that point right there. But y has to be less than or equal to, so I've got the left half of it, and z has to be greater than 1, so I've got the front half of it. Fine. So I've got the front half and the left half, so I've got the front left quarter essentially. So 1, 2, 3. So it's kind of like a stupid draw. And then it kind of comes at you this way. So it's kind of like a orange slice. It's like a quarter of an inch. Okay. All right. I think I've maybe not confused you guys more than you already might have been confused. I think I've maybe been helpful here. Good. I'm glad it helps. It can be challenging to describe these things. Yeah. I think those pictures that Grant has drawn also are helpful. If you haven't looked at them, I think you should. I think Grant is a much better drawer than me. Well, so your book does have some decent pictures. My older version of the book, maybe less so. Yeah, my older version's like, here's a cube, here's a circle, here's a sphere. Yeah, the book maybe not so excellent for this particular section. All right, I think that's all I'm gonna say about that stuff. Let's fast forward a little to section 13.2, I want to say, which, oh, where'd you go? Sorry, I'm just, oh my God, come on, computer. Don't go over there. Go back over there. All right. Sorry. Yeah, 13.2. So it looks like, yeah, so there's a few. I was talking about that. Okay, 13.1 actually, not 13.2. Another one. 13.1, mostly it's just stuff with this like vector valued functions kind of deal. So, like R of t might be some vector valued function like t cubed I minus 2t squared j plus 5tk. And then you can find the velocity and the acceleration vectors in the usual way, just by differentiating. The velocity vector is just 3t squared I minus 4tj plus 5k. And the acceleration vector is also not exciting. It is 6ti minus 4j plus 0k. Which I would maybe encourage you to write. Generally, I like to write the 0. Here, since you're going to write a vector, it's probably good to write the 0. You could also integrate R of t. You say, what's the integral from, I don't know, let's make it not terrible, 0 to 1 of R of t. The integration here is also just piece. This is actually in section 13.2, but it feels like it relates. So let's go here. So this would be the integral from 0 to 1 of this jazz. T cubed I minus 2t squared j plus 5tk. And you do just integrate piece by piece. So you're going to get t to the 4th over 4i minus 2t cubed over 3j plus 5t squared over tk. No plus a constant since it's definite from 0 to 1, and then you're going to plug in and you're just going to get 1/4 I minus 2/3 j plus 2 on the bottom, another t, 5 minus j. Is that particularly meaningful? Good question. My answer is probably no. All right, so look at this. Yeah. Yeah, there's nothing particularly exciting about that. Yeah, I'm trying to, I'm look. Yeah. It might. Yeah, I'm not seeing a particular, like the book doesn't seem to be describing a particular interpretation of what I mean. What I would guess, I don't know, and it probably doesn't matter. What I would guess is if you actually drew out this curve in three-dimensional space, which we can totally do using the, I didn't close it, I'm pretty sure, yeah, there we go. Let's see if we can make this work. This is gonna be, all right, it's gonna be maybe kind of cool. Maybe it's gonna suck. That's always a possibility in this class. But let's see if we drew this. So if we make R of t this function here, t cubed, and then y of t is 2t squared minus 2t squared. And then z of t is 5t, 52. And then let's move this around a bit. How can I move it around? Have I forgotten? Okay, there we go. And I don't remember what's what. I'm pretty sure, yeah, red is x, green is y, and blue is z. We go from 0 to 1. Probably not gonna be super exciting. There we go. Okay. So what I would guess is if you could follow this out, right? Like, that's right. If you could actually draw, if you could shade in like the area underneath it, I guess this is purely a guess, but I'm pretty sure it's right. Is that my guess, which is now sounding kind of wrong, is that the area would be this. That's the center. The area might be like the magnitude of this. I'm not really sure, to be honest. And I will also say the book doesn't really say much about it. I feel like I'm probably wrong at my guess because I feel like if there was something more to say, the book would actually say something about it. But yeah. So anyway, differentiation, anti-differentiation of these vector valued functions works kind of as we would hope it would. So the other thing I want to mention though is that sometimes we also look at my desk. My desk may not be lovely. Sorry, I'm very distracted today. It's probably the lack of sleep. There was a thing. I was like, teachers deleted mine. Let's see. Oh yeah, so I was looking at the Waldron's homework from section 13.1, and there were a couple of problems, just a couple, that give you the position of a particle in space at time t, and they kind of want you to find the functional equations. So like, let's work through these examples I'm going to talk about. Basically, we are reconstituting the function from the original parametric equation. If that makes sense. So here's one of the examples from the homework. This one could be kind of challenging. We'll work it out. So the equation R of t given by t over t plus 8 I plus 1 over tj is the position of the particle in the x-ray plane at time t. Find a function f of x of the graph y equals f of x is the path of the So y equals, we're looking for y equals x. So here's the deal. That's x. That's y. We essentially need to be able to take, usually if we're trying to write y as a function of x, it usually makes sense to try and find what x is equal to in terms of t, solve for t in terms of x, and then jam it into the thing that y is equal to. So here's what we know. We know that y, well, we know a lot of things. We know that y of t is 1 over t. We would like t to equal something in terms of x so that we can throw that in there. So let's see if we can make it happen. X equals t over t plus 8. Multiply both sides by t plus 8. Distribute. Bring this over so we can solve for t. So 8x equals t minus xt. Factor out the t. So t times 1 minus x equals 8x. So it looks like t equals 8x over 1 minus x. And then we can throw that in here, and y of t is going to equal 1 over 8x over 1 minus x, which will multiply is 1 minus x over 8x. Neat. So that's how we can write y as a function of x. Kind of cool. You might wonder if it actually works, right? Because you're kind of like, well, James, you did this stuff, and sure, maybe. So what's the easiest way to do this? How do we graph? The easiest way to do this would be to graph this and then to graph like y equals this and x equals this. I wonder if we can do that in Desmos. Let's find out. Sorry, if you guys are like the guinea pigs, this is the first time I've taught 21C not in person. A big surprise, I know. Let's find out though. Can we do parametric equations in Desmos? I don't know. I feel like the answer is probably no. Let's see. So you know what? Instead of trying to figure it out, maybe Google it. Let's see, parametric equations. A parametric graph in Desmos. Let's find out. So this is what I Googled. If you want to graph parametric equation, just make each coordinate function of t equal to domain. Okay. Oh, cool. So they've got it. So they're doing it as points. I see. Because I was going to try writing like y equals something of t, x equals something of t. That's kind of cool looking. I like that. Okay, so let's do this instead. So I don't want those. I want these. I want t over t plus 8. Versus, it's kind of fun. I will really, I think doing stuff in Desmos is just kind of fun. Also, as usual, I've written 2 instead of t, but we'll fix that. Get this right. Well, that looks bonkers. Let's let t get a little bit bigger. Let's go like 100. Okay, didn't give. Like, wow, it was so much more, James. Okay, that got stupid. I wonder why it gets bonkers when you go too big. I don't know, something's happening there. Anyway, it's not that important. Okay, let's see what happens if instead we graph y equals 1 minus x over 8x. Well, it seems reasonable, right? It seems reasonable that we're definitely gonna have a vertical asymptote at 0. And I feel like, let's see, well, it's probably gonna be different somehow, but let's find out. So I've always found, so I don't know if you guys know, but I can't figure out, like if you type the full numerator first and then try and make it divided by something, it does that. I guess you can put parentheses around it. And then that's dumb. Yeah, okay, see, that's why instead of doing all that, I usually do this. I start the denominator right away and then I go back and fix the numerator. 1 minus x over 8x. Yeah, it does look the same. However, and this is interesting, right? We don't get all of it. So I guess t doesn't have to be positive, right? So if I let t be negative, I'd probably get more of it. Ah, there we go. Yeah. So unclick this for a second. Let's see. Oh, that's weird that you missed like this part when you're missing. What the heck is going on there? Oh, that makes sense, I guess, right? Because so the y value is only negative if t is negative, right? Because 1 over t is only negative when t is negative. And the y value is positive when, yeah, so you're only getting, I see, neat. So you're only getting this part when t is positive, and you're getting all of this and all of this when t is negative. Oh, of course, because it's switching. So if x is t over t plus 8, t over t plus 8. Yeah, when is that going to end up being? Oh, sorry. So, yeah. Huh. Interesting. I'm trying to think about like, why is it positive over here, right? If t is between 0 and 1, good brain. I'm sorry, my brain is like having a hard time braining. If t, oh, sorry. I'm making a classic blunder here. I'm thinking of this as being t equals 1. This is not t equals 1. This is x equals 1. Right, so when x equals 1, yeah, we get the switch from being y being positive to y being negative. But to get x equals 1, t has to be, I don't know, to get x equals 1, oh, x can't be 1, right? Because t would be 8 over 0. Interesting. Anyway, I think we played with this enough, but that's kind of cool that you can actually graph these things and see that your function mimics what the parametric equation does. They do have differences though, right? Here, you can definitely see that x cannot be 0. Right? Right. But over there, well, actually, you also can't have x being 0. You could have t being 0, but oh, not really. So no, you can't. Excuse me. But it's interesting that you can never. So here's kind of the difference. Here it's totally legit for x to equal 1, right? That's totally fine. X is 1, y equals 0 over 1, or 8, which is fine. But up here, x cannot be 1 because this will never equal 1. Interesting. Okay. So yeah, we are limited, and that's often the case. In fact, let me give you guys another kind of easier example to see what I mean by this. I should point out, just to kind of point out what's important here, the important name of the game is you can use the parametric equation, solve for t in terms of x, jam that in for t in the y thing, and then get y as a function of x. But it is important to note that typically your parametric equation is often limited in some sort of way. Let me give you 2 examples which both show this. Let's say we have, and they're both going to be kind of the same. Let's say we had y equal to, sorry, my parametric, let's do it this way. We've got r of t is cosine of ti plus cosine squared of, we can have more fun. Let's just do the cosine squared of tj. This is pretty easy to solve for, right? If x of t equals cosine of t, you don't really need to solve for t here to be able to figure out what y is going to be, right? If y of t is cosine squared, that's just this squared, right? You could, right, say t is inverse cosine of x and then, right, plug it in for, that'd be silly, right? If you can see the straightforward answer, don't make it life harder. So then, great, we've got y equals x squared. But if we graph it, y equals x squared is everything. But I know something, and you know something about cosine. Cosine is limited in how big it can get. Cosine is between -1 and 1 always. So that means x is going to be limited to being between -1 and 1 because this is our x. So if we were graphing this, we only get this portion of it. And we often kind of talk about the direction things move in as time goes on. So at time equals 0, cosine of 0 is 1, cosine squared is 1. So we start here, and then as we move along, so time equals bigger than 0, bigger than 0, bigger than 0, time equals pi over 2. Pi over 2, cosine of 0, and cosine of 0, sorry, 0, 0. And then we keep going this way. Here we are going to be at t equal to pi. Cosine of pi is -1. Cosine of pi is -1 squared is 1. And then we keep going back and forth. So we go this way, and then we go back that way, and then we go that way, and we forever and ever and ever and ever until the end of time. Here's a similar but slightly different equation. What if we had r of t equal to e to the t, e to the t? Yeah, e to the t I plus e to the 2t j. Well, now we've got the same sort of situation. It's pretty straightforward, I think, to say that, yeah, of course, x equals e to the t, y equals e to the t squared, which is just x squared. You could also solve this for x, right? You could say, okay, t equals natural log of x, and then plug that in there for y, and y would be e to the t squared, which is e to the natural log of x squared, which is x squared. Again, we're going to be limited because e to the t is never equal to 0 or negative numbers. E to the t is always positive. So this one at time equals 0, if we're starting at 0, right? We can use negative numbers as well. But at time equals 0, x is going to be 1 and y is going to be 1. And then as time goes on, right, the time equals natural log of 2. Okay, fine. Be stupid, James. The time equals natural log of 2. You get the 0.2 comma 4. Right? Because e to the natural log of 2 is 2, and e to the natural log of 2 squared is 4. So this would be the 0.2 comma 4 when t equals natural log of 2. So we would get this kind of deal. We get that right half of the parabola. And then if you wanted t to be any real number, then you would get, so here's kind of the weird thing. All of this right here, that's t greater than or equal to 0. All of this right here, excluding the origin, all of that right there is t less than 0 all the way down to negative infinity. Kind of neat. So yeah, sometimes they want you to take a parametric equation and reconstitute the functional equation. However, typically not always, but you often lose something. And there was one, I think there was only 2 questions like this in the 13.1 homework assignment from Waldron's class. And the other one was slightly different. Let me take a look at that one real quick. The other one was, yeah, oh yeah. Yeah, this one looks terrible. So here's the other one, which, yeah, it's a little freaky. I've got the equation r of t equals 8 cosine of 9t I plus 2 sine of 9tj. And oh boy, I want to find a function f of xy, so the graph is the path of the particle. Now they do give you a hint here. They're not saying that you want, they're not saying this. They don't want you to try to find y as a function of x because you can't. They're saying they want this, f of x, y equals 1. Which should tell you really two things. Thing one, it's not going to be a function. We're going to have something with x and y equal to 1. Two, I got cosine and sine. I got it equal to 1. They're probably talking about a circle. Or worst case scenario, an ellipse. So what do we do with this? Well, here's what we do with it. What do we do with this? So first we just say this. We say that x, oh yeah, okay. Here's what we're going to do. X equals this. Y equals this. You really, really, really would rather have not these coefficients. So get rid of them. Divide both sides by 8. Or 2 in this case, right? So x over 8 equals cosine of 90. Y over 2 equals sine of 90. Now we know that sine squared plus cosine squared equals 1. So we're going to say, and it doesn't, as long, I should say, sine squared of an angle plus cosine squared of the same angle equals 1. Same angle, we're good to go. So we can say, hey, sine squared of 9t plus cosine squared of 9t. I don't know why. Usually, I always write my sine first, but I guess I should write cosine first. Fine. Cosine squared of 9t plus sine squared of 9t equals 1. So then, I'm going to replace cosine with this and sine with this. So I've got x over 8 squared plus y over 2 squared equal to 1. And I guess we could stop there. I would probably write it as x squared over 8 squared plus y squared over 2 squared equal to 1. And this equation is the equation of an ellipse. If x is 0, y could be plus or minus 2, right? Because 0 plus 2 squared over 2 squared is 1. So if x is 0, y could be 2 or negative 2. And if y is 0, x could be 8 or negative 8. That's the worst ellipse I've ever drawn, but there you go. So when you see cosine and sine, you should be thinking, I know that cosine squared plus sine squared equals 1. Okay. Angle stuff. Maybe we'll talk about angle stuff. Where was I going next? I know we don't have a lot of time left. I think. Sure. So I'm gonna start moving towards chapter 14, just talking about one domain and range kind of problem. For functions of 2 or 3 variables. It feels like a lot of these are functions of 3 variables. Okay. I'll give you guys kind of a very typical example, and then we will come back to this next week. So let's say your function, let's say z is a function of x and y. It's equal to the natural log, so passe. Let's try the log base, I don't know, log base 2 of, sure, why not? No, I don't want that. Let's do, sure, log base 3 of 81 minus x squared minus y squared. Fun times, how about all? And I want to find the domain and the range. By the way, finding the domain of this question definitely relates to the stuff we talked about in the beginning about describing what regions look like. So I know for a logarithmic function, the insides have to be greater than 0. And then typically, if you see an x squared negative x squared minus y squared, or I usually think of it as the negative of x squared plus y squared, we usually want that by itself. Same is true if you have like x squared plus y squared plus z squared. We kind of want that all by itself and everything else on the other side. Meaning I want to rewrite this as 81 is greater than x squared plus y squared. Or if you prefer, x squared plus y squared is less than 81. But we all know that x squared plus y squared equal to 81 is what kind of shape? A circle. Specifically, it's the inside. Oh, sorry. This is a circle centered at the origin of radius 9. And this is the insides of that circle, not including the boundary. So, right, this is like the point 9, 0. And here's my domain, everything inside this circle. How do I know it's everything inside and not outside? I tested a point. I tested the point outside. I tested the point 9, 9, right, which is definitely outside the circle, because if we go over 9, up 9, you've gone too far outside. But look, if you plug in 9 and 9, the inequality fails. 9 squared plus 9 squared is not less than 81. So 9, 9 is not in the domain, which means we're on this side of the border is the wrong side of the border, so we need to be on the inside. Okay. And then, so the domain is usually not too terrible, but I would point out the domain almost always is more than just an interval. It's not going to be like in Calc 21a, where you're like, oh, the domain is everything from like -4 to 5 or -infinity to +2, right? The domain is going to be some area in two-dimensional space in the xy plane. The range, on the other hand, if it's z is a function of x and y specifically, is going to be an interval like we're used to. How to deal with the range? So use your domain. We know that the domain, there's your domain right there. X squared plus y squared is less than 81. We also know, and this is key, x squared plus y squared is greater than or equal to 0, right? That's just true, unless you're dealing with imaginary numbers, which we are not. So take this, try and make it look like this. So first, I need negative x squared plus y squared. So -0, negative x squared plus y squared, negative 81. I multiply everything by -1, but when I multiply everything by -1, the direction of the inequality changes. Okay, but then I need 81 minus x squared plus y squared. So I'm going to add 81 to each side. So here's what I've got. I'm going to change this so it's this way. So I've got 81 minus x squared plus y squared is less than or equal to 81, is bigger than or equal to 0. And that seems totally reasonable, right? If we know that x squared plus y squared is less than 81, then 81 minus it has to be bigger than 0. And 81, if this is bigger than 0, 81 minus this has to be less than or equal to 81. And now the last part is to take the log base 3 of both sides, of all sides. So log base 3 of 81 is bigger than or equal to log base 3 of 81 minus x squared minus y squared is bigger than or equal to log base 3 of 0 isn't a real number, right? So you should think of this as the limit, right? As the insides go to 0, the log base 3 goes to -infinity. So our range here is -infinity to 4. Inclusive. Right? If x and y are both 0, we get log base 3 of 81, which is 4, because 3 to the 4th is 81. And if x squared plus y squared gets really, really close to 81, then the insides get really, really close to 81 minus 81, which is really, really close to 0. And as the argument of the logarithm gets closer to 0, we know that we have that vertical asymptote and we go down to -infinity.